In this fluid mechanics lecture, the discussion of macroscopic balances is continued. We will focus on situations that require a coupling of the macroscopic mass balance to the mechanical energy equation. We will introduce the quasi-steady state approximation, in which the unsteady mass balance is employed along with a steady form of the mechanical energy equation. We will illustrate this approach by considering the time it takes to drain a tank initially filled with liquid and related problems. So the first problem is shown schematically here. We have a tank of radius capital R and height capital H that's initially filled completely with liquid to the very top. The top of the tank is open to the atmosphere, which has pressure P naught. There's an outlet hole of radius R naught at the bottom of the tank, which is also, of course, open to the atmosphere. We assume that R naught is much smaller than the radius of the tank, so that the liquid level of the tank drops relatively slowly. The velocity of the liquid coming out of the bottom of the tank will be considered V2. That's something we have to find as part of the solution. The instantaneous height of the liquid in the tank is little h of t, and gravity is directed downward. We denote plane 1 as the top surface of the liquid at any instant of time, and plane 2 will be the outlet hole at the bottom of the tank. What we're asked to compute is the time it takes to drain this tank completely of liquid, T sub E. It can be time to empty or time for efflux, the efflux time T sub E. So in order to solve this problem, we first can consider a macroscopic mass balance. So if we look at the mass balance and apply it to the system, what we get is the time derivative of the total mass of fluid in the control volume is equal to minus the integral over all of the surfaces of rho n dot vs or rho n dot u minus vs. ds. So that's the general form of the macroscopic mass balance, and for reference we can look at our handout. We have the summary of the simplified macroscopic balances: conservation of mass, the time derivative of the volume integral of the density dV is equal to minus the surface integral over all surfaces of the system of the relative component of the velocity u minus vs dotted with n, which gives us a normal component rho ds. And we'll use this version here because it accounts for a moving control volume and unsteady behavior. So that's what we've written here. Now we just have to adapt this to the particular system shown over here at the right. So on the left-hand side, we get the time derivative of, well, rho times the total volume, V of t. And that's going to be equal to minus the integral over S, let's say the top surface, or S1, which is this plane 1, the top surface of the liquid. So the top of our control volume is going to move with the liquid. So if we want to illustrate the control volume we're choosing, our control volume is going to include all the liquid in the tank. That's our control volume V of t. So the control volume moves with the liquid. As the liquid drains out, the top surface of the control volume moves downward along with the free surface of the liquid. All right, so S1 is the top surface of the control volume, and we have rho n dotted with u minus vs ds, and we also have the bottom surface of the control volume, namely the hole at the bottom of the tank. We'll call that S2 of rho n dot u minus vs ds. And so now we can look at the left-hand side. Well, we have now the time derivative of rho times the total volume of liquid at any instant of time. Well, what's the volume? It's the cross-sectional area multiplied by the height. So it's pi r squared times h of t. On the right-hand side, on surface S1, the top of the control volume is moving, so Vs is non-zero, but it's moving at the same velocity as the liquid. So U minus Vs is equal to 0 at the top surface of the control volume, S1. And so this first integral term vanishes. Now if we look at the hole in the bottom of the tank, S2, well, that part of the control volume is not moving. So Vs is equal to 0. Moreover, N dot U we've denoted as V2 right here. And so V2 we assume to be constant over the cross-section of the hole. And this is a good approximation because it's open to the free surface. And the bottom of the tank is very thin, so it's not like we're flowing through a conduit where we'd have like a parabolic or other type of velocity profile for our laminar. It's just a liquid jet coming out. The jet has uniform velocity at V2. And so the right-hand side is equal to minus rho V2 multiplied by the surface area S2, which is simply pi R0 squared. So we look at this, we can divide by rho. We can also divide by pi. And we find that our mass balance simplifies to dH dt is equal to minus R0 divided by R, quantity squared, times velocity V2. And so that's the first important result we have. We have now a differential equation that tells us how fast the height of the liquid level changes, and it depends on, obviously, how rapidly the fluid is exiting the hole on the bottom of the tank. The next thing we have to do is figure out what is V2. And ideally, we can express V2 in terms of the height of the liquid, h of t, so we get a differential equation that involves only h that we can then integrate and solve to find h as a function of time. We can determine the time when h is equal to 0, and that tells us the efflux time or the emptying time for the tank. So in order to do this, we're going to assume that the liquid level in the tank changes slowly, such that it may be treated as quasi-steady. So this is what's called the quasi-steady state approximation, abbreviated QSSA or QSA, or sometimes just SS, but quasi-steady state approximation. What that means is we assume that h of t varies slowly. And as a result, we can use the steady form of the mechanical energy or Bernoulli's equation. Along with the unsteady form of the mass balance that we just derived. So in other words, we assume that any instant in time, because the height of the surface is moving so slowly, the height of the free surface of the liquid is moving so slowly, we can treat it as if it were constant when applying the mechanical energy equation. And this allows us to get an expression for the velocity V2 with which the fluid leaves the container. We can then plug that into our macroscopic mass balance, which incorporates the unsteady behavior, and then find a result. And that's why it's quasi-steady. It's a steady form of mechanical energy, or Bernoulli, coupled with the fully unsteady form of the mass balance. And more generally, in a quasi-steady state approximation, unsteady effects enter typically through boundary conditions. So just like Stokes flow is quasi-steady, because the fluid adjusts essentially instantaneously to any applied changes. So we solve a steady equation for the velocity field, but we can have time dependence enter through the boundary conditions or variations in the applied pressure gradient. So what we'll do first is we'll neglect also viscous losses. And so we can use the Bernoulli's equation. What we'll do is we'll take point 1 to be somewhere on the top surface of the liquid, and we'll take point 2 to be in the middle of the outlet hole. So if we apply Bernoulli's equation at steady state, and once again, if we want, we can look this up in our handout of the macroscopic balances. So we have 1/2 v squared plus p over rho plus gh is equal to constant. We can take the streamline connecting the top and bottom surfaces, top surface of the liquid in the middle of the hole, or we can use the irrotational flow version if we want as well. Doesn't really matter. Either choice gives us the same result here for Bernoulli's equation. It's just a question of how you quantify the error. So Bernoulli gives us 1/2 v1 squared plus p1 over rho plus gh1 is equal to 1/2 v2 squared plus p2 over rho plus g times h2. So v1 squared, that's the velocity of the top surface of the liquid. So if we were to write this out formally, we would have 1/2 times dh dt squared plus, what's the pressure at the top surface of the liquid? Well, from the normal stress balance, the liquid's in contact with the gas, so the pressure is just the gas pressure, P naught, divided by rho. Plus G, what's H1? Well, we'll use the bottom surface as corresponding to H equals 0, so the height of the top surface is just this H of T. Then we apply the same thing at position 2. We have 1/2 v2 squared plus the pressure at the outlet hole, which is in contact with the surrounding gas, is once again P naught divided by rho plus G times 0, because we take the reference plane for the gravity, for the potential energy, to be the bottom surface. You can take that to be anything that's convenient. It's convenient to set it equal to 0 at the bottom surface here. So we look at this now, we see that the P naught over rho terms cancel. This term is also 0. And then we're going to neglect this term, which is consistent with our quasi-steady state approximation. We're assuming the top surface of the liquid decreases in height very slowly. So the square of that change in height is going to be even smaller. So if we now solve this for V2, we find that V2 is equal to the square root of 2gh. So this is the second useful result. And this was first derived a couple hundred years ago, and it's known as Torricelli's law. That's where the word torr comes from as well, measurement of pressure. So Torricelli's law assumes a perfect interconversion of potential and kinetic energy. We're saying the kinetic energy, 1/2 rho v squared per volume, kinetic energy per volume, 1/2 rho v squared, is equal to rho gh, the potential energy of the liquid in the container. Setting those two things equal and just taking the square root, we find that V2 is equal to the square root of 2gh. So in the absence of viscous effects, we have the perfect interconversion of potential and kinetic energy. And that's what's known as Torricelli's law. So now what we can do for this problem is we simply take this value for V2 and substitute it into the expression we have for the mass balance. In the mass balance, we've eliminated velocity v2. We simply have the ratio of radii squared and square root of 2gh. So it's a differential equation for h that only involves h. There's no other variables in it because we've used Torricelli's law to substitute for v2. So when we do that, we now find that dh dt is equal to minus r0 divided by r, quantity squared, times the square root of 2gh. We also need an initial condition. Initial condition is simply that at time equal to 0, the liquid occupies the entire cylindrical container. So liquid height h of t is equal to capital H at time equal to 0. So our initial condition, h at t equals 0, is equal to capital H. First order differential equation, one initial condition, well-posed problem, we can solve it. So what we do is we just separate variables. So we take the square root of h and divide this side here. So we get h to the minus 1/2 dh is equal to minus r0 over capital R, quantity squared, times the square root of 2g dt. We can then integrate both sides. Integral of h to the minus 1/2 is 2h to the 1/2. And that's equal to minus square root of 2g r0 over r, quantity squared, times time, plus an integration constant we'll call c1. We can apply the initial condition to capital H to the 1/2 at time equals 0 is equal to 0 plus c1. So c1 is equal to 2 capital H to the 1/2. So if we put this back together, we find that substituting for c1, capital H to the 1/2 minus h of t to the 1/2 is equal to square root of g over 2 multiplied by r naught over r squared times time. So that's an expression for how the height varies with time. Now, if we want to find the efflux time, we just simply say that h of t equals te is equal to 0. And so the h of t term drops out, and we find that the efflux time, or exit emptying time, t sub e, is equal to the square root of 2 capital H divided by g multiplied by r over r naught quantity squared. So that's the time it takes to drain the tank. Also, for later reference, we can introduce a couple of things and write these things in dimensionless form. So, we'll use the same notation used in Bird Stewart and Lightfoot's. They denote by parameter n r divided by r naught to the fourth power. So this is something that's much, much bigger than 1. It's a dimensionless parameter, simply the ratio of the tank radius to the outlet hole radius, r to r naught raised to the fourth power. And so we can write this in dimensionless form as TE divided by the square root of 2h over g to the 1/2 is equal to n to the 1/2 power. Or another way to write this is T divided by 2nh over g to the 1/2 is equal to 1, TE, the efflux time. So that's the result we'll come back to in a few moments. For now, we'll just highlight this with a rectangular kind of thing, written at an angle there. The other thing we can do is we can write the solution for the height of the liquid at any time in a little more compact form. And so if we rearrange this expression here for the height, we divide by capital H to the 1/2, then just rearrange, we find that h of t divided by capital H is equal to 1 minus time divided by the square root of 2nh divided by g squared. So that's the analog of what we have over here. Time efflux, or emptying time, divided by 2nhg to the 1/2, and this is regular time divided by 2nhg to the 1/2 power. And we'll see why we've written it in this form in a few moments. And for now, just highlight this form as well. All right, so now we might say, what if the quasi-steady state approximation is not used? In other words, how can we assess the accuracy of the quasi-steady state approximation? In other words, what if we apply the unsteady form of the mechanical energy balance? Along with the unsteady form of the overall mass balance, which we've already used. So if we write this out, what we find is we have the time derivative of the total amount of kinetic and potential energy in the system. So we have the volume integral of 1/2 rho v squared dv, plus we have the volume integral of the potential energy, which is the integral of rho g z dv, and that's going to be equal to, well, minus the surface integral over surface S1 of 1/2 rho v squared plus rho g z n dotted with v minus vs ds minus the same thing written at the bottom surface, S2, minus the surface integral of 1/2 rho v squared plus rho g z n dot v minus vs ds, plus we have now the pressure terms, plus we'll write them in the simplified form. So we have P1 times the average velocity V1 times S1 minus P2 times the average velocity V2 times S2. And then we have the rate at which work is done in the system minus the compressibility term minus the viscous dissipation term. So what we're going to do now is just simplify this for our particular system. First of all, there's no work being done in the system by moving surfaces. There's no compressibility. Density is constant, so there's no compression work. And in the viscous loss term, we're going to approximate this as 0. We're going to neglect viscous losses. It'd be pretty hard to estimate these in this case anyway. All we have is the opening at the bottom of the tank. The water and the liquid in the tank moves downward very slowly. So approximating the viscous loss term, viscous dissipation term, as approximately 0 is very reasonable for the present situation. Once again, the velocity gradients are small in the system, so we'll assume that viscous dissipation is negligible. So we essentially have here now is the unsteady form of Bernoulli's equation, but applied to this control volume instead of just at 2 different points in the liquid. The question is now, how do we simplify this a bit further? Well, the one thing we note is that the pressure at surface 1 and 2, they're both open to the atmosphere, so the pressure at each case is P naught and P naught. We also know from the mass balance that the rate at which liquid exits the system is equal to the rate at which the top surface moves downward. So average velocity V1 times S1 is equal to the average velocity of V2 times S2 from the mass balance we considered previously. So this entire term involving the pressures is equal to 0 because the pressure is the same both the top and bottom surface. If the pressure weren't the same, this wouldn't go to 0, but in this case it does. The other thing is, let's look at surface S1. Well, on the top surface, the control volume moves downward at the same velocity as the liquid. So V minus Vs is equal to 0. Consequently, this entire integral vanishes over surface S1. And so what we're left with is the second integral over surface S2. We've already said we'll treat the bottom of the tank to be the origin of the coordinates in terms of potential energy or gravity, so Z is equal to 0 on the bottom surface. Moreover, the control volume is not moving along the bottom surface, so Vs is equal to 0. Finally, n dot V is simply equal to V2, and this becomes V2 as well. So this entire integral here becomes minus 1/2 rho times the average of V2 cubed multiplied by surface area S2, which is simply pi r0 squared. So finally now, we have to estimate the kinetic energy term per unit volume. What we're going to assume is that all the fluid in the tank moves downward at the same velocity. Now that's not exactly true, but it's a reasonable approximation given what little we know about the details of the flow structure. So we're going to assume that all the liquid in the tank moves downward at the same velocity as the top surface. And the velocity of the top surface is given by r0 over r squared times V2. So once again, as we said, we'll assume that velocity for the kinetic energy term is approximately R0 over R quantity squared times V2. And once again, we have that by saying we'll assume everything moves downward with the same velocity. The velocity of the top surface is dH dt, and that's the same as R0 over R squared times V2 with a minus sign, but we're going to square it, so it doesn't really matter. So that's where that term comes from. And then finally, we can evaluate the kinetic energy term simply by integrating. This would actually become the integral from 0 to 2 pi, integral from 0 to r, and the integral from 0 to h of rho g z dz r dr d theta, writing that integral out using cylindrical coordinates. This first integral here, with the velocity known and constant, or assumed to be constant throughout the domain of integration, we would simply get a 1/2 rho v2 squared r0 over capital R to the 4th multiplied by the volume v of t. So we can now just combine these simplified terms, and therefore what we get is the time derivative of the total kinetic and potential energy of the system, which we've estimated. So we get 1/2 rho v2 squared r0 over r to the 4th multiplied by the volume, which is pi r squared times h, plus the potential energy in the system, which is pi r squared times 1/2 rho g h squared. And this entire thing is equal to whatever's left on the right-hand side, which is simply this one surface integral here. So we get a minus 1/2. S2 is pi r0 squared. We have rho, and then we have velocity v2 cubed, because v2 is assumed to be uniform over the whole, and therefore the average of v2 cubed is just v2 cubed. So now we can combine this with the mass balance. So in other words, we can go back up to our unsteady mass balance, and we can substitute for V2. V2 will be minus R over R naught squared times dH dt from our mass balance. So we're not going to use Torricelli's law, because that was based on the steady form of Bernoulli's equation. The mechanical energy equation we're deriving now provides an alternative to that. So instead, we're just going to use our unsteady mass balance to substitute for V2. And we said that's equal to minus R over R naught squared times dH dt. So we'll substitute for this V2 here, and we'll substitute for V2 here, and rearrange the expression. So what we find, after we do that and do some rearranging, we get 2h of t times the second derivative of h with respect to t now, because v2 gives us one derivative. We substitute here, we're taking a second derivative, so we get two derivatives of h with respect to t minus n minus 1 multiplied by dh dt squared plus 2gh is equal to 0, where once again this parameter n is equal to capital R over R0 to the fourth, and that's something that's very big. We were assuming the hole is small relative to the radius of the cylindrical tank. So we have a second order differential equation in time, and so we need two initial conditions. So the first one is obvious, and it's the same as before, saying that h at time equal to 0 is equal to capital H. And we also need a second initial condition, because we have two derivatives, we just said, and so we need to specify dh dt at t equals 0. And what they do in the text is they assume that Torricelli's law holds its initial time. So we have 2g capital H times R naught over R squared. That's Torricelli's law at time equals 0. However, that's not the best choice. I think it's done because it facilitates a semi-analytical solution. So we'll get rid of this, and we'll assume that the initial rate of change of the height of the surface is 0. So in other words, as soon as we open the hole, that starts at time 0. So at time 0, the height's not changing yet. There's a transient period in which the flow must adapt and establish the velocity at the bottom of the tank through the mechanical energy equation, namely through the solution of this equation here. So we're going to solve these expressions here. So here's our second order differential equation for h as a function of time with our initial conditions. H at time equals 0 is capital H, and the initial rate of change of the height of the free surface at time 0 we're assuming is equal to 0. It takes a while for the flow through the hole to be established, and we can't assume that a steady state flow is already happening at time 0 like they do in the Bird, Stewart, Lightfoot text. Now we can also write this equation in dimensionless form if we like. We can say let phi equal h of t over capital H, and let tau equal time divided by the time scale. And time scale will be the square root of h over g. And then what we find is the differential equation becomes the second derivative of phi with respect to tau squared minus n minus 1 over 2, 1 over phi, d phi, d tau squared plus 1 is equal to 0. And we have phi when tau is equal to 0 is equal to 1, and d phi d tau when tau is equal to 0 is equal to 0. So that's just the equation in dimensionless form. We see the solution depends only on the parameter n, which is the fourth power of r over r naught. So the easiest thing to do now is we can solve this equation numerically. We can substitute and transform it into a system of two coupled first order differential equations, each initial value problems. We have the initial conditions for each, and we can integrate this in MATLAB using the same approach that we use, for example, for project 1, the shooting method for the Blasius equation, for example. In this case, it's very simple to do it. We can also introduce the events function, if we like, to find when the height goes to 0. And so we can therefore save the emptying or efflux time directly and run this in a loop. And I'll post the code that I used to compute this on the course website for those who are interested in glancing at it. What we'll do now is we'll compare the numerical solution to this equation for different values of n to the solution we derived previously for the efflux time. Namely, in dimensionless variables, the dimensionless efflux time is equal to 1 using the quasi-steady state approximation. And in our present case, we'll figure out what it actually is. So we'll go through here. And the first thing we do, we have two plots. The first plot, this is a plot of the height of the liquid divided by its initial height, capital H, as a function of dimensionless time. So it's time normalized by the square root of g over 2 capital H n to the 1/2 power. And we plotted this for different values of n, ranging from 5 all the way up to 1,000, and the heavy dashed line is the quasi-steady state approximation we derived before. So we can see quasi-steady state, we go monotonically from 1, or for height of 1 to height of 0, we hit 0 at a dimensionless time of 1. We can see for the actual solution, the smaller n is, the greater the discrepancy there is between the actual curves and the computed or the predicted curve using the quasi-steady approximation. However, once n gets close to 100, between 50 and 100, the curves for the change in the height or the height's location as a function of dimensionless time are essentially indistinguishable from the quasi-steady state result. So n between 50 and 100 corresponds to the radius of the hole being approximately 1/3 of the radius of the entire tank or smaller. So if the hole is 1/3 the size of the tank, that's a pretty large hole. And yet, even for that large hole, the quasi-steady state approximation looks very accurate. We can get a little more insight by plotting the exit velocity, or the efflux velocity v2, normalized by the square root of 2gh to the 1/2 power, as a function of dimensionless time. Once again, the heavy dash curve is the quasi-steady state approximation, and the other curves are the real curves computed using the unsteady form of the mechanical energy equation. Still some approximations, the way we estimated the kinetic energy of the entire system and neglected viscous dissipation, but this is much more realistic than the quasi-steady approximation. Once again, we can see there's a greater discrepancy for small n, which is a very, very big hole, and as n gets larger, meaning the hole gets smaller compared to the radius of the tank, the agreement with this quasi-steady approximation becomes very good. What we can see, however, though, is in the unsteady form of the mechanical energy equation, there's this initial transient period where the velocity goes from 0 at the initial time until it establishes a velocity that eventually becomes consistent with what's predicted by the quasi-steady state approximation. But once again, once n is close to 100, meaning the hole is 1/3 of the diameter or radius of the tank or smaller, there's very good agreement except for this very short initial transient period. And if all we want to do is compute how long it takes the tank to empty, this initial transient period is not of any concern. But let's zoom in on this region a little bit more and just see what's going on. So here we go. We can see for n equals 100, by time of about 0.02 in dimensionless units, we've almost attained exactly the quasi-steady state approximation. And if n is any bigger, meaning the hole is even smaller, this initial transient is very, very small. It's just an adjustment from initial velocity of 0 when the hole's first opened up until the essentially quasi-steady state velocity, which is the prediction of Torricelli's law. Quasi-steady state approximation assumes, once again, that it's quasi-steady, so it assumes steady state behavior initially from the mechanical energy or Bernoulli's equation. So in that case, it assumes that Torricelli's law is established instantly at the very first instant time. So as soon as that hole is opened, it assumes the velocity is immediately equal to the square root of 2g capital H. In reality, as we've seen, and as we've mentioned a couple of times, there is this transient period it takes for the velocity to adjust. And that's what's captured in the actual numerical solution here. But once again, when the hole is 1/3 of the size of the tank or smaller, there's very, very good agreement with the quasi-steady approximation. And finally, I plotted now here the normalized exit emptying or efflux time, TE, divided by 2nh over g to the 1/2 power, that's the dimensionless time. Plotted that as a function of n. So for the quasi-steady state approximation, this value of the emptying or efflux time should be equal to 1 in dimensionless units. So the quasi-steady state approximation would always predict the value of 1. And we can see here, even when n is very small, so when n is even equal to 5. And so if n is equal to 5, we can see that 5 to the 1/4 power is 1.5 approximately. So if the hole in the tank is 2/3 the size of the tank, then the time it takes to empty the tank is 94% of what's predicted by the quasi-steady approximation. So even in the extreme case, the hole is 2/3 the radius of the tank, which is a humongously large hole, then the efflux time predicted, or the actual efflux time, is still 94% of the quasi-steady state approximation. So there's only a 6% error for a huge, huge hole. And as the hole gets smaller and smaller, meaning n gets bigger and bigger, we see that we asymptote to the value of 1 predicted by the quasi-steady state analysis for the dimensionless efflux time. And once again, once the hole is about 2.7 or 2.8 times smaller than the radius or diameter of the cylindrical tank, the efflux time is within 1% of the value predicted by the quasi-steady state approximation. And we can see how much more effort there was in using the full form here, trying to do the unsteady form of the mechanical energy equation, which necessitated, in this case, a numerical solution as well, versus the 5 or so minutes it took to do the algebra for the initial problem using the quasi-steady state approximation. And so the result is, as long as the hole or exit pipe size is relatively small compared to the size of the tank, the quasi-steady state approximation is extremely accurate for tank emptying problems. So as long as the hole is not as big as the entire tank, we can use the quasi-steady state approximation with good certainty and a high level of accuracy. And so the take-home point is we will use the quasi-steady state approximation for tank emptying problems, because the difference between the sort of almost exact solution using the unsteady form of the mechanical energy equation and the approximate solution using the quasi-steady state approximation, which is unsteady mass balance coupled with steady state mechanical energy or Bernoulli equation, the difference between those two things is essentially negligible for any problems of practical significance where the holes or the pipe sizes will be exiting a tank will be much smaller than the size of the tank themselves. And so we can always use, for the purpose of this class, the quasi-steady state approximation for tank emptying problems.